in a situation like the one we've just seen, if we let y stand for the volume of the cube and x for the dimensions, let's say the radius of the cube, and if we assume, let's let y stand for the volume of the sand pile and x for the radius of the sand pile, then we see that if we double the radius, we're going to do 2 times 2 times 2 times the volume. Because again, if we imagine that the pile is constructed of little tiny cubes, and we inflate those cubes so that they grow in all 3 directions, in order to increase the diameter in both the directions the diameter spans, and also to increase the altitude, it should be clear that we're going to have to cube that factor 2. Or if we increase by factor 3, we're going to have to cube that. Now, without going into a lot of detail about why, let's just see that it works. In that case, we say y is proportional to x cubed, because it grows in the 3 directions, and we write y equals kx cubed to designate that proportionality. If we had another quantity that was proportional to x squared, we'd write y equals kx squared. If we had something that was inversely proportional, we'd write y equals k times 1 over x. If we say y is proportional to x, we simply write y equals kx. So we have this way of writing proportionality. Now we have this data. X stands for the diameter of some sugar piles that we observed, and y stands for the number of containers that we added. This is not on the scale that we used with the meter stick and the piles that you saw in the previous video clip. So this is probably not going to have the same units as that one. Okay? X was measured in something besides centimeters in that case. In any case, and actually X was the average radius of the pile, not the average diameter. But in that case, we had this data. Now, if we assume that y is proportional to x cubed, and it's not absolutely certain, those piles might have changed shape slightly, and if they change shape, then this proportionality might not hold. Okay, this proportionality assumes that all the cubes that make up the small sand pile grow proportionally to make up the big one, so the big one is going to have exactly the same shape, just a different size compared to the small one. In any case, we have this data. In order to evaluate k, well, it's very simple. We take any data point and plug it in here, and we're going to get a value for k. So if we plug in 6.3 for x and 1 for y, k turns out to be approximately 0.004. Substitute 7.9 for x and 2 for y, k turns out to be, again, approximately 0.004. Although for these 2 points we end up with approximately 0.005. Just to see how that calculation works. Okay, for this data point we had x equals 8.6 and y equals 3. We just plug those in and solve for k. K ends up being 6 over approximately 636.0047, which we rounded off to 0.005. Now the point here is that k is about the same for all of these data points, although there are some significant difference. 0.004, 0.005, there is a 25% difference in those values.